Today we will see some of the properties of inverses of matrices. If A is a non-singular matrix, determinant of A inverse is equal to the reciprocal of the determinant of A. Already we have seen if A is a non-singular matrix, inverse exists. That means always determinant of the A inverse will be equal to 1 by determinant of A. Let A be a non-singular matrix, then determinant of A will not be equal to 0 and A inverse exists. Whenever determinant of A is not equal to 0, A inverse exists. Now, by definition, we can write like this. A matrix is multiplied by its inverse, you will get identity matrix. Now, using the product rule, we can write like this. Take a determinant of all the terms. Now, using the product rule, we can write like this. Here, determinant of A into A inverse can be written like this. Determinant of A into determinant of A inverse. This is because of the product rule of the determinants. Then when we take the determinant of the identity matrix, it will be equal to 1. From this step, we can write like this. Determinant of A inverse will be equal to 1 divided by determinant of A. So whenever A is a non-singular matrix, determinant of A inverse will be equal to 1 divided by determinant of A. Determinant of A inverse is equal to the reciprocal of the determinant of A. This is one of the properties of the inverses of matrices. Now I will show this using a 2 by 2 square matrix. A is a non-singular square matrix. So its determinant is obtained by multiplying these two numbers, 4 into 5, 20, minus 2 into 3, 6. So 20 minus 6 is 14. So determinant of this matrix is 14. So it's a non-singular matrix. Now our aim is to show that determinant of A inverse is equal to the reciprocal of the determinant of A. Now A inverse is obtained by this formula, adjoint A divided by determinant of A. Determinant of A already we know, 14. Then adjoint of A can be obtained by finding the cofactors. The cofactor of this 4 is 5. Cofactor of this 3 is 2 with a negative sign, because this 3 is in the first row, second column. So 1 plus 2, 3, odd number. So we have to change the sign. Next, cofactor of this 2. Delete this row and this column, 3. So this 2 is in the second row, first column. 2 plus 1, 3, odd number. So that's why negative sign. Then cofactor of this 5 is 4. Cofactors of the elements of this row is written as the second column. So adjoint of a matrix is the transpose of the cofactor matrix. Now before taking the determinant, this 1 by 14 is to be taken inside. So when this 1 by 14 is taken inside, you will get a matrix like this. Then you find out the determinant of A inverse. Find out the determinant of A inverse. So in a determinant, if an element is common in a particular row, it can be taken outside. So this 1 by 14 is taken outside. Since it's again in the second row, again it is taken, so it is a 14 square. After taking this 14 outside, the remaining element 5 minus 3 minus 2, 4. So here it is square because in a determinant, if an element is common in a particular row, it can be taken outside. Now 1 by 14 from this row it is taken and from this it is taken. So that's why it's 14 square. Now 1 by 14 square. Now determinant of this 5 into 4, 20 minus 6. So 14 by 14 square. So 1 by 14. Now it's very clear. Determinant of A is 14. Determinant of A is 14. Determinant of A inverse is 1 by 14. So from this is clear. Determinant of A inverse is equal to the reciprocal of the determinant of A. Now let us see another property of the inverses of matrices. If A is a non-singular matrix, then A transpose inverse will be equal to A inverse transpose. Here first we are taking the transpose, then taking the inverse. Here we are taking the inverse, then taking the transpose. Both are equal. Now, as per the definition of the inverse, we can write like this. A matrix multiplied by its inverse will be equal to identity matrix. Now we are going to use the reversal law of transposes. If you take a transpose of all the terms, using the reversal law of transposes, you can write like this. It will get reversed. See, A into A inverse transpose. When you remove this bracket, it will get reversed. So A inverse transpose into A transpose. That is because of the reversal law of transposes. When you remove this bracket, it will get reversed. Then when you take the transpose of the identity matrix, there will not be any change. So it will be identity matrix itself. Now from this, we have to use a technique. See, A transpose. When it is multiplied by A inverse transpose, you are getting identity matrix. That means inverse of A transpose is this one. So mathematically we can write like this. A transpose inverse will be equal to A inverse transpose. See, here you see A transpose. When it is multiplied by this, you are getting identity matrix. That means this is the inverse of this. That means inverse of A transpose. Inverse of A transpose is this one. That means A inverse transpose. So A transpose inverse is equal to A inverse transpose. Now I am going to show this property by a 2 by 2 matrix. This property is A inverse transpose is equal to A transpose inverse. Now I will take a 2 by 2 matrix. This sum already we found out A inverse. A is a 2 by 2 matrix. Its inverse. In a previous sum I showed this. A inverse is 1 by 14, 5 minus 3 minus 2, 4. Now same matrix, first I will take the transpose. 4, 3, first row is written as the first column. 2, 5, second row is written as the second column. Now you got A transpose, you find the determinant of A transpose, that is 14. Then you find the inverse of that A transpose, you will get like this. Then already we got A inverse, you take the transpose of that. Now you can see these two are same. That means A inverse transpose is same as A transpose inverse. Another property of inverses of matrices. If A is a non-singular matrix, lambda A inverse will be equal to 1 by lambda A inverse. Here matrix is multiplied by lambda, then taking the inverse. Here After taking the inverse, you are multiplying by 1 by lambda. Both are equal. Now let us see the proof for that. By definition, we can write like this. A multiplied by its inverse will be equal to identity matrix. Now, lambda is a non-zero scalar. From this expression, we can write like this. Multiply by lambda, divide by lambda. So, there is no change in the expression. Multiplied and divided by same number, lambda. Then, that is equal to eigen. These two terms, you multiply by lambda and divided by lambda. So, there is no change. Now, from this expression, you can write like this. This matrix, when multiplied by this matrix, you are getting identity matrix. That means inverse of this matrix is this one. That's why you are getting identity matrix. So by this we can write like this. Inverse of lambda A is this one. So 1 by lambda A inverse. Inverse of this matrix is this. That's why we are getting identity matrix. So using equation we can write like this. Inverse of this matrix is this one. So lambda A inverse is this. So 1 by lambda A inverse. Now we will see this property by an example. This side A is multiplied by lambda and taken the inverse. This side first taken the inverse, then multiplied by 1 by lambda. This lambda is a non-zero scalar. So the given matrix A is multiplied by 2. So for lambda I have taken 2. So in our case lambda is 2. When this matrix is multiplied by 2, you have to multiply each element by 2. So 4 into 2 8, 3 into 2 6, 2 into 2 4, 5 into 2 10. Then we have to take the inverse of this matrix, lambda A inverse. So we have to take the inverse of this matrix. So determinant of this matrix is, so inverse is given by the formula adjoint A divided by determinant of A. So we have to get the determinant of this matrix. 8 into 10, 80 minus 24. That is 56. Then you have to get the adjoint of this matrix. Cofactor of this 8 is 10. Cofactor of this 6 is 4 with a negative sign. Cofactor of this 4 is 6 with a negative sign. Cofactor of this 10 is 8. So we can get the inverse of this matrix. Inverse of a matrix is given by adjoint of the matrix divided by the determinant of that matrix. So we found out the inverse of this matrix. So take this 1 by 56 inside, so you will get like this. So this side, first A is multiplied by 2, then taken the inverse, you are getting like this. Then already we got the inverse of this matrix. In a previous sum, we got it. Inverse of this A inverse is 1 by 14, 5 minus 3 minus 2, 4. Then this side, that inverse is multiplied by 1 by lambda. In our case, lambda is 2. So you multiply by 1 by 2. Already there is 1 by 14. If it is multiplied by 1 by 2, it will become 1 by 28. Then this 28 is taken inside. 1 by 28 is taken inside. So you are getting this. So here, first we found out the inverse, then multiplied by 1 by 2. Here, first we multiplied by 2, then taken the inverse. You can see both are same. That means lambda A inverse is same as 1 by lambda A inverse.